So our goals for this video is first off to define limiting reagent and excess reagent. We're going to define mole ratio, and then we're going to determine the limiting reagent, the excess reagent, and the amount of the excess reagent left over for both an everyday life problem and a chemical problem. We're going to start with kind of silly examples where we're not using chemistry at all, just to get down the problem-solving skills, so that when you move to the chemistry problem, it's not really anything new. This is a problem, these types of problems, students will often sort of miss the forest through the trees, and that'll help us out with this. So if it seems a little silly, just stick with me through it. So first off, let's define what a limiting reagent is. This is a reactant in the chemical reaction that limits the amount of product that can be formed. We know that when reactants react, they react in very particular ratios. Now, if you put in that exact amount of ratios of those reactants into a beaker, then there won't be any reactants left. But that's not typically how experiments are run. Typically, you have an expensive reactant and a cheap reactant, so you just put in a little bit of the expensive one and a ton of the cheap one to get your result. Or maybe you don't know how these were mixed and you want to find that out. There's lots of different things that can happen here, and this is a very important concept. And it's going to be important not just in this class, but in all your future chemistry classes and a lot of your biology classes. So then the other ones are the excess reagents. That's the ones that are not limiting. In real life, this is typically your things that are relatively cheap or relatively unreactive or cause no problems, things of that sort. So we want to know a couple of things about this, not just what the excess reagent is, but how much is left over. By definition, there won't be any limiting reagent left over, but there will be excess reagent. And then lastly, we'll talk about mole ratios in here too. And so this is your ratios of your reactants that react to form a certain ratio of the product. And so we get this from the chemical equation. So let's start with our sort of everyday silly example problem. So let's say that we're making gift bags for our little brother's birthday. And we want to make sure we have the same amount of toys in every one. Otherwise, kids fight. So you've got to make sure you have the same amount in each one. You sit down and decide that you're going to have two cars, 3 pieces of candy, 4 pirates gold, and 2 dinosaurs. And that's going to make a gift bag. So you go to the store and you buy enough to do this. The thing is that the bags come in different groupings. So instead you get 10 toy cars, you get 25 pieces of candy, you get 22 pieces of pirates gold, and you get 11 toy dinosaurs. And we want to say, well, how many gift bags can we make out of this? You need to make sure you have enough to be able to, have the right amount of bags. So from this, we can look and we can say, well, if we have 10 cars and we're going to put 2 in each bag, we can get 5 bags. If we have our 25 pieces of candy and we want 3 in each bag, we're stuck with 8.3 bags. If we have our 22 pieces of gold, but we want 4 per bag, we can only get 5.5 bags. Or for our dinosaurs, if we have 11, but we want 2 per bag, we can only get 5.5 bags. And this tells us our limiting reagent because we know which one limits our amount of bags. Well, the cars do, because we can only get 5. And that's what stops us from being able to make more bags. It's the one that we run out of first. So that sets up our first part of the problem. Now, you might be saying, well, why did you solve for bags? Couldn't you say, well, if I have this many cars, how many pieces of candy do I need? How much pirates gold do I need? How many dinosaurs do I need? And yeah, you could do that too. It's a matter of personal preference. Now, let's talk about what that means as far as excess reagents go. So we know that cars are going to limit us. We know that if we try to make these bags, we only can get 5 bags from the cars. That means we're out of cars, which means that that's our limiting reagent. That's going to be all used up. Now, how much of the rest is left? Let's think about how we're going to do this. We would know how much we start with, and we know how many we use per bag, so we know how much we use up. So let's start with our candy. We had 25 to begin with. We made 5 bags. So if we made 5 bags, how much candy did we use up? Well, 15. So if we want to see how much we have left over, we take our starting amount and we subtract off how much we used. And we're left with 10 candies. The important part here is that you're paying attention to how we're solving the problem. You can all get these answers without help, I know that. But people will make all sorts of silly mistakes when you go to do the chemical problems, adding or dividing instead of multiplying or subtracting, all sorts of things. And if you keep this in mind, the only thing that makes any sense to do here is to take the 25 candies minus the 15 that you used up. And we're going to be doing the identical thing when we do the chemical problem. So now take a second and finish up and do this for the pirate's gold and the dinosaur. So let's go with the pirate's gold. We start with 22, and we want to see how much do we use up. We have 5 bags. And so we're going to say, okay, well, we used 20. And we know that we have the 5 bags because that was what our limiting reagent told us. So we used up 20 pirates gold making the bags, which means that we have 2 left over. 22 minus 20 is 2. Now the dinosaurs. We started with 11 that we bought, and we put 2 dinos per bag, and we had 5 bags. So that meant that we used up 10 of them. Since we used up 10 and we only had 11 to begin with, we're left with just 1. So now let's take this exact same formula, this exact same protocol, and do it for our chemical reaction. So here we're going to have, I'm going to start as simple. I'm going to start us with moles, and then we're going to work up to a little bit more complex. So we're starting with 2 moles of methane, which is the CH4, and we're going to burn it in the presence of 16 moles of oxygen. So now, unlike some of the other problems we've done, I've given you a direct amount of every single reactant, which means that we don't know which one's going to be limiting. We have to look at it. And it's not always just the lowest one. So that's a common misconception that comes up, that I'll just look at the lowest one. Not always, and that's because of the way that the mole ratios work. So let's work through this. What is our limiting reactant? And then I also ask how many moles of CO2 are made, and then how many moles of the excess reagent are left over. When you do this, you're going to start the same way that we did with the gift bags, where we say for each reactant, how much product can we make? So let's first act as if all of the methane reacts. If all of the methane reacts, we have 2 moles of methane, and for every mole of methane, we get 1 mole of carbon dioxide. Now, why did I solve for carbon dioxide instead of water? Well, for solving for the limiting reagent, it doesn't matter at all. The reason I picked to solve for carbon dioxide is because the next part of the problem asks you for carbon dioxide, so it saves us a little bit of work to just solve for that one instead of the water. Now let's do the same thing as if all of the oxygen reacts. So we start with our 16 moles. Now we have a different mole ratio because it takes 2 moles of oxygen to get 1 mole of carbon dioxide, and we get that from the coefficients in the chemical reaction. Overall, this leaves us with 8 moles of carbon dioxide. Now, we know we don't form both of these. One has to be right, and it's always going to be the lowest one because we're going to run out of methane first. The methane's going to be all used up. And then we just have all this leftover oxygen that wasn't needed. So our total amount made is 2 moles of carbon dioxide, and our CH4 is our limiting reactant. So now for the last piece. How many moles of the excess reagent are left over? So we're going to start here by using our methane. Because our methane is our limiting reactant, our methane tells us how much of our oxygen actually gets used up. So let's walk through each of these step by step. Oftentimes students will want to do this in 2 pieces, and that's okay. I just put it all in one. So the 16 moles, where does that come from? That's our initial amount of oxygen. That's how much we started with. If you think back to our non-chemical example, that's the amount of dinosaurs that we bought. Now we're going to subtract how much we used up. To figure out how much we used up, we need to start with our limiting reactant. So this is like saying we made, 5 gift bags. And those were limited by the cars. The cars is what decided how many dinosaurs we used. Just like here, the methane decides how much oxygen we use. So we start with our 2 moles of methane. and we say, okay, for every 2 moles of methane, for every mole of methane, you're going to use 2 moles of oxygen. So that conversion factor I put in there is based on the coefficients in front of the chemical equation. We have a 2 in front of the oxygen and a 1 in front of the CH4. So everything in that parentheses is how much oxygen is used up. So we have 16 moles minus 4 moles is 12 moles of O2 left over. I made this simpler by starting with moles. Generally, you'll actually have to start with grams, and so we're going to do an example of that next. So very similar, but now I have 2 grams of methane burnt in the presence of 9 liters of oxygen that was at STP when we started. So first off, what is our limiting reactant? We're going to do the same thing, except now our conversion factors are a little bit more complicated. So we start with our 2 grams of methane, but this time we have to convert from grams into moles. And so I divide by the molar mass. So that 1/16 is the molar mass of methane. From here, it's the same as the last slide. We convert between moles of methane and moles of carbon dioxide. So it's a 1-to-1 ratio, and we get 0.125 moles of carbon dioxide. Let's do the same thing for oxygen. We started with 9 liters at STP. So we have to kind of go back to maybe even high school is the last time you saw it. The conversion factor for gases at STP. And that's every 1 mole is 22.4 liters. And that's true for all ideal gases. So a bit of review there. So we have our 9 liters divided by our 22.4 liters in order to get to moles of oxygen. Once we have moles of oxygen, we need to convert into moles of carbon dioxide, and so we use our mole ratio, which is 1-to-2. And this leaves us with 0.20 moles of carbon dioxide. So we look at this and we see which one's lowest, and it's our methane again, and so our methane is once again our limiting reagent. So from here we have a couple of different, I changed up the problems a little bit. And I said, how many moles of carbon dioxide are made? We have that part. Then if cooled to STP, how many liters of CO2 would be present? So I want us just to convert back into liters. And since we haven't had gases yet, we can only really do that at STP. So we're going to do a very similar thing to what we did before. I'm going to start back from scratch and say that we have our 0.125 moles of CO2, and we're going to multiply that by 22.4 liters. Now, why did I ask you to do that? A lot of these problems are going to have you changing things at the end to particular circumstances. Maybe it's liters, maybe it's grams, maybe it's something else. But you need to be able to just kind of add on different pieces. And this was a slightly different piece. It's liters instead of grams. So we had 2.8 liters of CO2 made. So now for our last step. How many grams of excess reagent are left over? So this is going back to our kind of similar formula that we did in the first 2 problems. We need our initial moles of oxygen that we had, and we want to subtract off our moles of oxygen that we used up by reacting the CH4. So walking through this step by step, we have our 9 liters of oxygen. We need to know how many moles that is. So we divide that by 22.4 to get our moles of oxygen. From here, we subtract off our amount that's used up by the methane. So walking through that step by step. The 2 grams of methane tells us how many methanes we started with. We divided by the 16 to get to moles of methane. And then we use the mole ratio of oxygen to methane to get to our moles of oxygen. So that first grouping is the moles of oxygen that we started with. The second grouping is the moles of oxygen that we used up. We subtract those and we get 0.152 moles of oxygen left over. So we have our amount that we started with, We have our amount that we used up to give us our total moles. Now, I didn't actually ask for moles. I didn't actually ask for moles, I asked for grams. So we have one last conversion factor to do. We'll take the 0.152 moles of oxygen and we'll multiply that by the molar mass to give us our grams of oxygen. So we're all done with this problem, but I do want to make a comment that there is many ways we could do this. So I happen to do everything in moles just to stay consistent. But if you had wanted to do this subtraction in liters, you could. If you had wanted to do it in grams, you could. These conversion factors can be done at any step of the problem. You just need to make sure that when you do the subtraction, that you subtract the same unit from the same unit. So in summary, we have our limiting reagent, which is the reactant in the chemical reaction, which we run out of first. It keeps the amount of product limited. We have our excess reagent, or reagents, which are all the other ones. So those are the ones that are left over after the reaction has finished and we've run out of the limiting reagent. We have our mole ratio, which we use to solve a lot of these problems. That is our coefficients in our balanced chemical reaction. And we can compare the mole ratios to solve for the limiting reactant and solve for the excess reactants and the amount of the excess reactants left over.